Welcome back, dear students. So we are continuing the session in thermodynamics. So today, in this video lecture, we are going to discuss about a very important thermodynamic property known as pressure. All of you will be having a feel of what pressure is. We might sometimes experience pressure in our daily life itself, isn't it? But from thermodynamic point of view, let us discuss what pressure is. So, a very simple example or the experience what we have or which comes to our mind when we talk about pressure is the tire pressure and the gauges which used to measure the pressure in tires, right? In your childhood days you used to pressurize your bicycle tire using a hand pump, right? You are pressurizing the air filled in the cylinder of the hand pump using that handle into the pressure through the valve, isn't it? So let us discuss the pressure from thermodynamic point of view in the following slides. So the definition of pressure is like this. From a physics or thermodynamic point of view, the pressure is defined as the normal force exerted by a fluid per unit area. So it is a normal force perpendicular to the surface at which it acts, exerted by a fluid. So pressure is the force exerted by a fluid. So what is the counterpart of pressure in solids? That is stress. Yes, studied in strength of materials or mechanics of solids. It is having the same mathematical expression, force by area. Pressure is also expressed mathematically as force by area, but it is a normal force exerted by a fluid per unit area. So as from the definition, you can see the units as Newton per meter square, which is commonly known as Pascal after the scientist Pascal, whose law governs the pressure measuring devices as well as many other systems in which pressure is the major pressure plays the major role. So since the unit Pascal is too small for pressure to encountered in practice, we use kilopascals or megapascals with the proper prefixes, m for mega and lowercase k for kilo. So many other units, especially in tire pressures, you might have come across is PSI, pounds per square inch. So we will see the relationship among these units also, as well as some of the pressure measurement devices and some equipments which works based on Pascal's law and the variation of pressure. Okay, so let us proceed further. So in this figure you can see a very chubby person as well as a slim person. So a slim person will be experiencing very less pressure on his foot, right? In his feet he will be having very low pressure of 3 psi because his weight is only 150. Weight is acting downwards, right? W acting downwards, and here you can see even the area of the feet which is in contact with the ground is the same in both the cases, but a chubby person, a fat person is having a very high weight when compared to a slim person. He will be experiencing more pressure on his feet, more pressure on his feet. Similarly, you can do a simple experiment. Two have a feel of pressure, what pressure is, by taking a pencil, a sharpened pencil, and by applying force on either side of the pencil by keeping it horizontal. So you can see a higher pressure on the tip of the pencil since it is having a very less surface area. So force by area. Even though same force is applied, if the area is lesser, the pressure will be higher. If the area is more, the pressure will be less. So pressure is a consequence of effect of force, normal to the force. So similar example for pressure, the more number of tires in a truck carrying a heavy load will be more, because in order to have additional contact so that the pressure will be distributed among the tires, and sharp edged knife to apply more pressure so that objects will be cut. Then the pressure acting on a high heel footwear and a flat footwear. There will be high pressure since the area of contact is very less, but here the area of contact is pretty high, so pressure will be less. So these are the common day-to-day examples we experience regarding pressure. Now let us see the relation between various units. First, the relation between bar and Pascal. Bar is another unit for pressure. So 1 bar is equal to 10 to the power 5 pascals. Similarly, atmosphere is another unit for pressure, which is related to Pascal, as 1 atmosphere is equal to 101,325 pascals or 1.01325 bars. Similarly, other unit in CGS system is kilogram force per centimeter square. Kilogram force per centimeter square. It is equal to 9.807 into 10 to the power 4 pascals, or which is equivalent to 0.9807 bar or 0.9679 atmosphere. Please have a note of all these things, because in your questions, problems, numerical examples, many units will be given. The pressure will be given in different units. You have to convert those units into SI system, SI units, before starting the calculation. Now, let us see different types of pressures. Different types of pressure. You may wonder, why so many pressures? So actual pressure at any point is usually denoted as absolute pressure. Actual pressure at a given point. But that is not the pressure which is measured using a gauge. That is not the pressure measured using a gauge. You have a pressure gauge to measure the pressure in your vehicle tire. So it will read a value in psi or Newton per meter square or kilogram force per centimeter square, whatever the unit may be. That is the pressure known as gauge pressure. If it is above atmospheric pressure, it is gauge pressure. If it is below atmospheric pressure in outer space, that is known as vacuum pressure. Right? So here, let us discuss about the relation among absolute pressure, gauge pressure, and atmospheric pressure. So for any property to be measured properly, there should be a reference. So that reference level is termed as absolute vacuum or the absolute zero, where the pressure is measured to be 0 Pascal or 0 bar or whatever it is. That is absolute pressure. Now, the pressure experienced at the mean sea level is termed as atmospheric pressure, which is denoted by this dashed line here. Atmospheric pressure. So the pressure with reference to the absolute vacuum experienced at the atmospheric pressure is termed as atmospheric pressure. Now, all these gauges, whether it is pressure gauges or vacuum gauges, these gauges are calibrated, or these gauges will be measuring pressure with respect to the atmospheric pressure. All these gauges are calibrated by setting zero pressure when the atmospheric pressure is attained, that is at the mean sea level. So when the pressure gauge reads 0, that means it is 1 atmospheric pressure. Fine. If the pressure gauge reads negative, that will be vacuum pressure. If the gauge reads positive, that is positive pressure, that is above atmospheric pressure. So you can see here. So these relations could be summarized like this. The absolute pressure is the sum of atmospheric pressure plus gauge pressure in the case of positive gauges, positive pressures. If the absolute pressure is equal to atmospheric pressure minus gauge pressure if the pressure is negative pressure, negative gauge or vacuum. Now pressure at any point in a fluid is same in all directions. That is very important property of pressure. Pressure at any point in a fluid, whether it is gas or liquid, it is the same in all the directions. That means the pressure is a scalar quantity. Pressure is a scalar quantity. Now when you go down in a fluid, the pressure increases linearly. Pressure increases linearly, and that pressure difference is directly proportional to the depth or height of the fluid column, as well as it is proportional to the density of the fluid. So that height difference or the vertical distance delta z, I will show you the diagram, that is sometimes used as a measure of pressure known as pressure head. So you can see here a container, a jar contains a liquid which is open to the atmosphere at the top. At the top surface of the liquid, the atmospheric pressure is acting, where the pressure is atmosphere. When you go down in the fluid liquid, for example for a height of h, the pressure will be atmospheric pressure plus density multiplied with acceleration due to gravity multiplied with the height at which we are measuring the pressure, rho gh. So this rho gh is having the units of pressure. Rho gh is having the units of pressure. Rho is the density, g is acceleration due to gravity, and h is the height of the liquid column, or the difference between 2 points in a liquid. Now coming to the gases, gas is also another fluid, right? For small to moderate distances, the variation of pressure with height is negligible because of very low density of gases. When compared to liquids, gases are having very low density, rho. For example, for air, the density is of the order of 1 kilogram per meter cube. But for water, it is 1000 kilogram per meter cube. Right? So because of the low density of gases, the variation of pressure with height is negligible for small to moderate distances, especially in the case of tanks filled with gases or cylinders. We can consider the pressure to be uniform throughout the cylinder or the container. Now, before stating what is Pascal's law, let us see a container having an irregular shape like this. There are different points marked here: A, B, C, D, E, F, G, as well as H and I. So A through G are, if you notice, you can see here that are on a same horizontal level. A, B, C, D, E, F, G are on the same horizontal level. That means, and these points are also connected with the same fluid, water. These are connected with the same fluid, water. That means these points will experience the same pressure. There won't be any deviation in pressure at these points, A through G. But if you notice, the point H and I is connected with water, but H is connected with mercury. Even though H and I are situated at the same level, they will experience a different pressure, because at point H, mercury is filled, and point I, water is filled. So even though these 2 points are at the same horizontal level, they will experience different pressures because of different fluids. So you can conclude from this analysis that when an irregular container, if connected with the same fluid and the same points in that container which are situated on a same horizontal level, will be experiencing same pressure. And when you go deep in the same fluid of constant density, the pressure will be increasing. Now, the Pascal's law states that the pressure applied to a confined fluid, that means confined fluid, pressure fluid contained in a container, it is confined. Okay, pressure applied to a confined fluid increases the pressure if you apply some pressure to that confined fluid. So that pressure will be increasing throughout, irrespective of the direction. In all the directions, the pressure will be increasing by the same amount. That is the very working principle of a hydraulic lift. You can see here the point 1 and 2 here. Point 1 and 2 are at the same horizontal level, as well as these are connected by the same fluid. So obviously 1 and 2 will be having same pressure, right? P1 equal to P2. Now what is pressure? It is a normal force exerted by the on a fluid by unit area, right? Unit force, normal force exerted by a fluid per unit area. So F by A, mathematically it is F by A. So at point 1 it is F1 by A1, and point 2 it is F2 by A2. Or we can get the ratio of forces F2 by F1 is equal to A2 by A1, where A2 is larger and A1 is smaller. That means by applying a very small force here in this smaller area, we can have a larger force, so that we can lift the car in a garage. That is the very working principle of a hydraulic lift. Clear? Now, how to measure pressure? This is the simplest device to measure pressure, known as manometer. It is simply a glass tube or plastic tube of U shape. So here, if you want to measure the pressure of gas inside this tank, you know that in a gas, the variation of pressure with depth, height is negligible. So you can consider the gas pressure throughout this container to be same. Now, the working principle of manometer is like this. So you consider a reference point, a reference line. So here I have drawn a reference line 1 to 2. Okay, 1, 2 is the reference line here, which are connected by the same fluid. So please note that when you are taking the reference line, some points to be noted is a reference line should be connected with the same fluid. So here 1 and 2 are connected with the same fluid, and 1 is the interface between the two connecting fluids. So these 2 points to be taken care, to be noted, to be kept in mind while taking the reference line. Okay, so P1 equal to P2. You know that since these are connected by the same fluid. Maybe mercury, heavier fluid, or lighter fluid also. Depends on how much pressure it is in the tank or pipeline to which the manometer is connected. Now P1 equal to P2, where P2 is the, here since the limb of the manometer on the right hand side is open to atmosphere, at this point atmospheric pressure will be acting, and for this height, for a height of H, that is P2, the pressure will be atmospheric pressure plus the pressure due to this fluid for a height of H, rho G H, rho of this fluid in this black color, gray color, G and H. That will be the pressure experienced at this point, which is the pressure at point 1 will be same as that in pressure 2. So by noting down the pressure at point 2, you will be able to evaluate the pressure at point 1 and thereby the pressure inside this tank for the gas. Got it? I hope it is clear. If you have any doubts, please use the comment section below to comment, to post any queries or doubts or questions. Now, you may have to use multi-fluid manometers. So in that case, different heights and different densities of the fluids will be different, right? So at point 1, at the bottom of the tank, the pressure will be, P1 will be the atmospheric pressure, that is P2, okay, plus rho 1 into G into H1 plus rho 1, rho 2 into G into H2 plus rho 3 into G into H3 will be the pressure at point 1. So here P2 means the atmospheric pressure. Fine. So multi-fluid manometers may have to be used if very high pressure or complicated geometries are there where we need to measure the pressure. So for example, here we have a tank containing water and top of which air is there. Okay. So point 1 is at the interface of air and water inside the tank, and various heights are shown H1, H2 and H3, and there is a multi-fluid manometer like this which contains 1, 2. There are two fluids. So first fluid is water here, and you have oil as well as mercury. Fine. If you want to measure the pressure at point 1, you have to do a detailed analysis. So two things have to be noted. 2 points when connected with the same fluid on a horizontal level will be experiencing same pressure. When you are going down in a fluid column in a tube, the pressure will be increasing. These 2 points are to be kept in mind when solving such complicated problems. So here in this case, we are equating the pressure at point 1 and 2. At equilibrium, this pressure will be balanced. Okay, the atmospheric pressure will be acting here. As a result of the pressure of water inside the tank, this height of these columns, that is H1, H2, H3, will be different. Okay, if the atmospheric pressure is pretty low, what will happen? This fluid will rise. If the atmospheric pressure is high, what will happen? This will, H3 will be pretty less. It will come down. The mercury will come down. So the analysis is like this. We are starting either from 1 or 2. So let us start from P1. Okay. So P1 plus rho of water G into H1. So this point here, you can see here, and the same point inside this tank will be experiencing same pressure. So if you analyze the pressure through for this vertical distance and the vertical distance inside this column, it will not make any difference, right? It will get cancelled out, because here the pressure will be increasing downwards and here the pressure will be decreasing. When you are moving up in a fluid, the pressure will be decreasing. Okay, so this level, this line is taken as the reference line for the first term, that is rho into G into H1. So P1 plus rho into G into H1. So this much height water pressure will be acting at this point. Okay, so this much height water pressure will be acting here. So this point and this point will be having same pressure. That's why we are taking the pressure due to the height of water in the tank, that is the pressure acting at this point for a height of H1, that will be same at this point inside the column, manometer column. Fine. Now the next term is connected with the pressure due to oil. So oil is filled in this light shaded portion. Fine. So this point and this point are connected with oil, so it will be experiencing same pressure. So we are neglecting this entire portion. Now the remaining portion for a height of H2 will be having a pressure, again it is coming down, fine, due to the height of the oil H2. So rho 2, that is rho of oil into G into H2 for this much height. Now this point, this dark shade, that is mercury, this point and this point will be having same pressure. So this entire section of the limb of the manometer could be neglected, because the increase in pressure will be compensated by the decrease in pressure here on the right side. Now for a height of H3, the pressure will be decreasing since we are moving upwards. We have started from 1, we are coming like this, and here we are moving upwards in the last column, which is filled with mercury. So minus rho of mercury into G into H3, minus rho of mercury into G into H3, equal to atmospheric pressure, equal to atmospheric pressure, that is acting downwards, that is acting downwards. So we are equating the pressure on the left and right side of the limbs of the manometer. Fine. Thereby we will be able to evaluate the pressure P1, the gauge pressure. We will get the gauge pressure, the absolute pressure here. We will get the absolute pressure P1. If it is gauge, it will be mentioned P subscript G. If it is simply uppercase P, that is absolute pressure. Here, if you are considering the atmospheric pressure to be 0, that is 0 reading in a gauge, we will get P1 to be gauge pressure, P gauge. Then it will be P gauge. So that is the working principle of a multi-fluid manometer. It is not at all complicated. It is very simple. If you understood two key points, that is when you are going down in a fluid, the pressure increases, and 2 points on the same horizontal line connected with the same fluid will be experiencing same pressure. These 2 points, if you are kept in mind, understood properly, then it is very easy to analyze. Now there is another device, pressure measurement device known as barometer, which is exclusively for measuring atmospheric pressure. Only atmospheric pressure could be measured using the manometer. So with that, we'll stop for this session on pressure. If you have any questions, any doubts or clarifications needed on any of the slides or topics, please use the comment section below, and keep watching, enjoy, and share with your friends, those who are interested to know the basics of thermodynamics or other topics which are listed in the playlist. Please keep watching, subscribe and like. Thank you.